Okay, hello again. This is the presentation for algebraic proof, and I'd like to start with a lovely little puzzle for you. Have a look at this following algebraic proof that 2 equals 1. It cannot be true, can it? But please, if you can, find where the mistake is for me, because it all makes a hell of a lot of sense to me. We start with the assumption that A equals B. Now this isn't an impossibility in the maths world. For example, a third can equal 0.3 reoccurring, or 2 squared can equal 4. So two things can look very different but in fact be equal, and that is the case with A and B. So let's start by assuming that A equals B. Let's multiply both sides of that equation by A, giving us A squared equals AB. Let's then subtract b squared, giving us a squared minus b squared is ab minus b squared. Let's now factorise. Now they've done a difference of two squares factorisation on the left hand side. I hope you recall that from factorisation, and they factorise the right hand side, they factorise b out. And so after that, can you see what they've done? They've divided by the bracketed term a minus b, and they're left with a plus b equals b. They've then substituted from the first line a equals b, remember, so they've made that a become b, so we have b plus b equals b, and therefore 2b equals b, divide by b, 2 equals 1. What's wrong with that? I can't see a thing wrong with that, can you? Well, I'm going to give you a little hint here. What numbers are mathematicians banned from dividing by? Do you remember the answer? I'm sure you do. It is 0. If you start dividing by 0, you end up with things like 2 equals 1. Yeah, that's why mathematicians aren't allowed to divide by 0. Now, did I divide by 0? Well, yes, in fact I did, going from the 4th line to the 5th line down. Now you'll say, but you divided by a minus b, to which I would reply, but we assumed that a equals b, and if a equals b, then a minus b, the bracketed term, must equal 0, no matter what the value of a and b, because a equals b. Therefore, that was the point where we introduced an error. Yeah, a plus b can't equal b on the next line down unless a equals 0. Yeah, that in itself is an impossibility, apart from the fact that a equals 0. But then we're saying that a equals b, and therefore 2b equals 1. 2b equals b. Now that can also be true in the case that b equals 0. Then we've divided by b. Now obviously if b is 0, then we've divided by 0 again, and we've ended up with 2 equals 1. So there's two possible places there where we've divided by 0. It's it's a lovely little puzzler, and it will confuse, I think most people. It certainly confused me the first time I saw it when I was challenged to find the mistake. And yeah, okay, so let's go through a fairly straightforward example of algebraic proof. Let's look at how we're going to prove that the sum of any two odd numbers is even. Now, any two odd numbers, well, let's remember that they can be different odd numbers, like 7 and 193, so we have to use different letters for each of our odd numbers. So I've used 2m plus 1 for my first odd number and 2m plus 1 for my second odd number. You'll only need to do that in these kind of questions if you're talking about two entirely different numbers. Consecutive numbers where you can express it as n plus 1, so on and so forth. So we're using 2m plus 1 because that's naturally an odd number, because it's one more than an even number, and an even number would be anything times by 2. So when we think about it, if we now just add those two expressions together, we're simply going to get 2m plus 2n plus 2 after we've a bit of tidying up. Factorise out the 2, that's important, that step as well, and you're left with 2 brackets m plus 1. I'm not really too bothered about what's in those brackets, because m and n, remember, they were really whole numbers. Yeah, we defined that just after we stated it, and you must really state that, otherwise we're dealing with fractions possibly, or negative numbers, irrationals, who knows. Yeah, but provided they're whole numbers, 2 times whatever's in the brackets is going to obviously be an even number, and therefore we've done our proof. Trickier example would be something like this. Prove the product of two consecutive odd numbers is always 1 less than a perfect square. Okay, let's have 2m minus 1 and 2m plus 1 this time. I can always use minus 1 as well as plus instead of plus 1. The reason I've done it is because I'm then using difference of two squares, and I know how this bracket's going to multiply out. It's going to end up being 4m squared minus 1. Now you must use this last step at the end, and I hope you can see why. At the moment, with 4m squared minus 1, all you know is that it's definitely 1 less than 4 times a square number. And that's not what we're trying to prove. We're trying to prove it's 1 less than a square number. That's all a perfect square is, a square number. So if we have something squared minus 1, that's when we've proved it. And that's exactly what we do in the last step. We actually square root the 4m squared, if you like, or find the square root of 4m squared. It's naturally 2m, and we put that in brackets, squared. That's how we've achieved it this time, and it's important, that last step. If you want to see a very difficult example of this, you can have a look at the extension question at the end of the scheme of work for this week. That extension question, I'll quickly mention it now, is prove that the product of 4 consecutive integers is always 1 less than a perfect square. Now that was actually a question from many years ago from the British Mathematical Olympiad. It's supposed to be quite difficult. If you feel really confident with factorising polynomials of cubic degree or quartic degree, you can do that, especially if you like grid method multiplication. I'd love to show you the answer to that if you do get round to having a go at it and you find it very tricky. If you find an interesting way of doing it, I'd love to see your answer as well, so please do post it up on the forum. Anyway, let's have a look at linear sequences and nth term. Have a look at the following 2 sequences. I'm pretty sure you remember how to do this, so pause the video whilst you think about it. Give me the nth term for the following 2 sequences. All we do is look for the common difference, yeah? Because, well, like the first one, it's +3 each time. So if I'm teaching like the kind of student who finds this quite difficult at first, and plenty of people do, it's not obvious, to be honest. What I would do though is think, okay, we're adding 3 each time. What times table adds 3 each time? The 3 times table. Now 3 times table goes 3, 6, 9, 12, 15, and its nth term would be 3n. Well, our sequence is just 4 more for each term in the 3 terms table. 7 is 4 more than 3, 10 is 4 more than 6, 13 is 4 more than 9. So all we need to do for this one is 3n plus 4. That seems, most students get the hang of that very quickly as well. The one which goes backwards is a bit tougher, but it really works very similar. Okay, so with the second one, it's certainly tougher. It's going down 3.5 each time, so it's just like the 3.5 times table, but it's going to be negative as well. And if you think about that, the nth term for minus 3.5n is going to be minus 3.5, minus 3, minus 7, minus 10.5, so on and so forth. Now you've got to think, what do you need to go from minus 3.5 up to 33, or minus 7 up to 29.5, or minus 10.5 up to 26? That common difference there is what we need to add on the end. It's going to adjust it and move the minus 3.5 times table, if you like, up to 33, 29.5, 26, 22.5, so on and so good. So, okay, that's linear sequences dealt with. What about quadratic sequences? Now, this was a funny topic because it was part of like higher level key stage 3, like year 9 kind of material for a bright set, and it kind of dropped off the syllabus for GCSE, and it's not actually in the syllabus at A level. So I could understand if you haven't seen this before. I think when I came back to teaching, I hadn't seen this in a long time. I hadn't seen this since I was at school, because it didn't really pop up at uni either when I studied it. Not this particular method anyway. So yeah, when I saw it in the textbooks, I must admit I was scratching my head at first thinking, I don't remember this. But yeah, so have a look at this, see if you've done this before. These are 3 sequences, have a look at them. Try and find the nth term if you like, if you want to pause and really get stuck into it. But if you haven't seen it, you might want to watch first technique, because there is quite a sort of a not long method, but yeah, you know, a little bit involved. But yeah, just have a look at these 3 sequences and see if you can tell me what they all have in common, because they're all quadratic sequences. So what is it which defines a quadratic sequence? Have a pause. So, okay, I hope you noticed that they all increase at a steady rate. Well, what do I mean by that? I mean that whilst they are getting bigger and bigger and bigger, that bigger and bigger and bigger is increasing constantly. What I'm really saying is that if I look at the first difference for each sequence, it's jumping, yeah, it's going plus 3, plus 5, plus 7, plus 9 for the first one. Second one, it's going 4, 6, 8, 10. So both of those seem to be going up by 2 each time. And the third one goes 2, 6, 10, 4, 14. So the third one, well, you want to get students to look at this first difference and second difference business, because if the second difference is constant, it's quadratic. You can also tell them actually, and I'm sure you probably guessed this by extension, that if the third difference is constant, it's cubic. If the fourth difference is constant, it's quartic, and so on and so forth into the higher level polynomials, which they will certainly look at in A-level maths. So yeah, you could mention that, but they will only ever have to deal with, at the worst, quadratic sequences. You could get them to do a little bit of work on cubic sequences, see if you can figure out a way, as a little investigation or a project. If you've got a very bright class, you could certainly ask them to see if they can find a method for finding cubic sequences. But yeah, let's move on. What are we going to do with that second difference? Well, there is a rule here which it's worth declaring to the students. If you want to try and prove this rule, I applaud that. I really do. I think that's excellent of you, and perhaps quite ambitious, or perhaps not. Perhaps you think, as many maths teachers do, that everything should be proved. I personally, when I'm teaching this at GCSE, I steer clear of the proof of that, and I try and prove a lot of things, just because I've often found that this is a sort of topic which I don't find straightforward anyway. So I haven't been that ambitious yet, but I do applaud anybody who wants to try and prove things down to the finest detail. Anyway, that second difference is crucial to this solution. If the second difference is 2 or 4 or 3 or 6 or 9, you need to halve that second difference. That coefficient, that value, is crucial to this method. Now, I've put star n squared in for step 2. That star will stand for half of the second difference. Yeah, you need to multiply n squared by half of the second difference. Now, most of the time that second difference will be 2. If it was 1 though, you would still need to halve it. If it's 3, whatever number it is, you need to halve it. So when the second difference was 4, that is actually going to be a 2n squared. N squared is what we need, just 1n squared. Now construct the following table. Let's write down our nth term sequence. I've just written down the second sequence actually. I'll explain why I think the first sequence is easy in a second. But the second sequence goes 3, 7, 13, etc. And then write down 1n squared, the sequence for that underneath. Now this trick is lovely, because if you now subtract, and you can subtract either way around, and I ended up with 2, 3, 4, 5, 6, 7. Now that means, if you really think about it, that means that the nth term minus n squared equals this linear sequence. And I know how to put that linear sequence in terms of n, because the nth term for that sequence is simply n plus 1. So nth term minus n squared equals n plus 1. Now all I've got to do is add over the n squared to the other side of the equals, and I've got my nth term expression. It's a lovely trick. Okay, let's do the same thing, just one more bit of practice with the last set of numbers, which went 1, 3, 9, 19, 33 and 50. If you want, you can pause the video and have a go at it on your own first, but I'll quickly run through it now. Okay, so we've got 1, 3, 9, 19, 33, 51. 2n squared is what we're going to have to use this time, so that gives us the following list of numbers: 2, 8, 18, 32, 50 and 72. Once again I'm going to subtract. This time I'm going to do it the other way around, 2n squared minus nth term, because that way I don't produce any negatives. And once again I get a linear sequence, and 1, 5, 9, 13, etc. has an nth term of 4n minus 3. So 2n squared minus nth term equals 4n minus 3. Now simply rearrange it into nth term again, and you've got the quadratic sequence. You can check it works as well. Let's look at the fifth term in our nth term sequence. Well, fifth term is 2 times 5 squared minus 4 times 5 plus 3, and it's 33. Voila. Fantastic method, I'm sure you'll agree. Now the reason why I didn't bother doing the first one is because if we just flick back to the first one, we've got 2, 5, 10, 17, 26 and 37. Well, I don't think I'd even bother looking at first and second difference there. I think I'd probably just think, is it close to the square numbers? And the fact is, it's really close. It's 1, 4, 9, 16, 25. Well, that means that this sequence is just 1 above that, and so this sequence is clearly nth term is n squared plus 1. Very straightforward. Okay, I hope you enjoyed that, and I suspect that maybe for some people that would have been quite useful, because certainly if I'd seen it after university, and that was after studying a maths degree, well, I hadn't actually seen that method before, so when I came into teaching it was completely brand new to me. And this is what I mean about subject knowledge, and your subject knowledge is always going to be enhanced whilst you do the job, to be honest, because you're going to meet lots of different methods and lots of interesting tricks and interesting proofs and things which just fascinate you. So yeah, I hope this was quite useful and perhaps quite interesting as well. Okay, I will speak to you all soon again. Bye bye.